magnetic nanoparticle. Magnetic nanoparticle is a material ranging from size from 1 to 100 nanometer. It is a material made from magnetic material. It can move by applying magnetic field, which means that it is affected by magnetic field. There are three types of magnetic nanoparticles. The first one is oxide. For example, is ferrite. The second one is metallic. The example of metallic nanoparticle is cobalt. And the third one is metallic with shell. For example, cobalt with graphene shell. There are several types of methods that can be used to synthesize magnetic nanoparticle. First is co-precipitation. The second one is hydrothermal. The third one is laser pyrolysis. The fourth one is microemulsion. And finally, a combustion synthesis. Now, let's see how magnetic nanoparticle was made using hydrothermal method.
Now, these particles can be easily pulled around with a magnet, and they are the basis for a lot of my research. The reason for this is because of this property, you're able to manipulate them in whatever liquid or fluid you want. And by building things onto them, you can accomplish really cool things. So I'm using this for nanorobotics and all kinds of really cool systems that I'll be showing in future videos. This is just one easy example of accomplishing a task. To make them, you'll need two ingredients, ferric chloride and some green tea. We're going to be using a hydrothermal method. So to start, we're going to have to make just a regular cup of green tea. Here I'm using deionized water in an Erlenmeyer flask, but a jar and tap water will work fine. In this example, I'm using 100 ml of tea and 3 ml of iron chloride, but feel free to play with the concentrations. Then load it into a hydrothermal reactor. I showed and explained both of these in a previous video. And then load it into an oven at 180 degrees and leave it for 10 to 24 hours. When it's done, let it cool, and when you go to open it, if it worked, lots of gas will come out, but be careful and do this slowly. When it's all done, you're left with amazing magnetic nanoparticles.
There are two properties in magnetic nanoparticle. First is physical properties. To observe the nanoparticle size, we can see from the relationship between conductivity versus nanoparticle radius. Magnetic domain can be defined as volume of ferromagnetic material in which all magnetons are designed in the same direction by the exchange by force. Magnetron can be defined as a spinning electric charge particle which create a magnetic dipole. When size of ferromagnetic material is reduced below a critical value, it becomes a single domain which has uniform magnetization that causes the particle to be smaller. Multiple domain has non-uniform magnetization that cause the particle size become larger. When size of single domain particle further decrease below a critical diameter, the conductivity becomes zero and such particle becomes super paramagnetic. Under an external magnetic field, domain of a ferromagnetic nanoparticle align with the applied field. The magnetic moment of single domain super paramagnetic nanoparticle align with applied field. In the absence of external field, ferromagnetic nanoparticle will remain at a magnetization, where super paramagnetic nanoparticle will exhibit no net magnetization due to rapid reversal of magnetic moment. There are several applications that use the concept of magnetic nanoparticle. First, industrial application. Magnetic nanoparticle commonly used as synthetic pigment in paint and ceramic. Second is biomedical application. It is used in vitro and in vivo application. And third, environmental application. It involves in removal of organic and inorganic pollutants. Now, let's watch the video for application of magnetic nanoparticle.
Cancer is when you have one cancer cell and it divides to form another cancer cell, and another, and pretty soon this happens uncontrollably, and this is what forms tumors inside our body. And these are bad, and we want to get rid of them. Two ways doctors are trying to do this now is through chemotherapy and radiation therapy. But these aren't the most optimal, because these methods also attack healthy cells in your body in addition to the cancerous ones. And this is what causes you to lose your hair. So how are these nanoparticles going to work? We're going to take our nanoparticle and fill it with our cancer drug right there. And then we're going to attach a targeting ligand to the surface of the nanoparticle. And I'll explain how these work in just a bit. Once we do this, the nanoparticle is injected right into the bloodstream. Here's what it looks like. Above and below the bloodstream on the left side are all the healthy cells. These are the good guys, which we want to keep alive. The nanoparticle can't attack them because of this tight junction blood vessel, which prevents our nanoparticle from reaching them. On the right hand side here are all the cancer cells, which we want to attack. And how do we do this? Well, all these cancer cells have a receptor ligand on their surface and are surrounded by leaky blood vessels. This is good because it allows our nanoparticle to have access to these cancer cells as it makes its way through the bloodstream. So, as the nanoparticle nears these cancer cells, the targeting ligand on its surface can bind to the receptor ligand on the surface of the cancer cell and cross the leaky barrier to eventually kill it. This is the big thing that separates treatment with nanoparticles from chemotherapy and radiation therapy. Because of all this, we're going to reduce the amount of healthy cells being attacked as well as increase the amount of cancer cells that die.
Here, the researchers are working on a solution to that problem with nano-sized particles and a magnet.
The magnetic nanoparticles are very tiny, small particles, and the size of the particle is about 10 nanometer. We code the chemistry specific to phosphate. So when you add those particles into the wastewater containing phosphate, those particles will absorb phosphate. Then you can use the magnet to separate the particle from the wastewater. And now the water can be discharged without phosphate.